In this video, I'm going to talk a little bit about transformations of signals that are defined piecewise. Transformations of signals defined piecewise are conceptually no different from signals that are just defined by one analytical expression for the entire range of values of time. But sometimes if you are asked to write analytical expressions for the transform signals, when signals are defined piecewise, there can be a little bit of a difficulty, and this is exactly what I want to address in this video. And the best way to do this is to take an example. Let us say I have a signal x of t, which is defined to be 2 times t if t is greater than 0. It's defined to be negative t if t is less than 0, and it's defined to be equal to 0 at t equal to 0. Okay. Now, let's say we want to find an expression for x of negative t. And using that, I would like to find an expression for half of x of t plus x of negative t. Now, a little bit later on in the course, you will see that this is also what is called the even part of the signal x of t, but that is not particularly relevant for this example right now. Okay. Now, if you're asked to solve a problem like this, it's relatively easy and straightforward to sketch the function x of t first. Now, if I sketch the function, the function looks like this. It has a slope of 2 for positive values of t, and it has a slope of negative 1 for negative values of t. Right? And then I can simply flip this about the y-axis, and then I can get my signal x of negative t, and there is nothing really difficult about this. But what I'm really interested in is in not actually doing this pictorially, but let's say I want to directly write a mathematical expression for x of negative t. Okay. Now, of course, all I have to do is to replace t by negative t to obtain x of negative t from x of t, right? So I could write x of negative t to be 2 times negative t. But the important thing I want to point out in this video is, what do you do to the range of values of t over which this expression is valid? Now, if you think about this a little bit, you really have to replace t by negative t even for the range of values of t. And that is the point that I want to make with this video. So x of negative t is really defined to be 2 times negative t for negative t being greater than 0. And x of negative t is defined to be negative of negative t for negative t less than 0. And it's equal to 0 for negative t equal to 0, but of course that's the same as t equal to 0. Now, if you think about these different range of values of t, now I can rewrite them in terms of inequalities involving t instead of negative t, right? So particularly, we could rewrite these and write x of negative t, in fact x of negative t to be equal to negative 2t. If negative t is greater than 0, this inequality turns into t being less than 0. And this is equal to t for t being greater than 0, and it's equal to 0 for t equal to 0. Okay. Now, once I have an expression for x of negative t, I can combine the expression for x of t and the expression for negative t together. So I can take this, I can combine it with this to write an expression for half of x of t plus x of negative t. Now, one thing when you do this, I have seen some students make the following mistake when they try to add x of t and x of negative t. You have to be very careful to add only the expressions for x of t and x of negative t that are both defined over the same range of t. So for example, when I add the two of them together, for values of t less than 0, what I should really get is negative t from here and negative 2t from here, because these are the two expressions that are defined for t less than 0. Okay, don't forget that you cannot add the 2t with negative 2t. Okay, so then of course half of x of t plus x of negative t would be equal to negative 3 over 2 times t for t less than 0. It would be equal to 3 times t over 2 for t greater than 0, and it would be equal to 0 for t equal to 0. Okay, and in fact you can see pictorially also you will get exactly the same thing. If I were to simply take this signal x of t, and if I were to flip it about the y-axis, I would get a signal which looks like this. You know, the slope here would be negative 2 and the slope here would be 1. So when I add, so this is x of negative t. And really, if I were to write an expression for this, so x of negative t is equal to t for positive values of t, and it's negative 2t for negative values of t. So similarly here, this is negative t and this is 2t and this is 0. So when I add them up together, I get 3t for t greater than 0 and negative 3t for t less than 0, and half of that is negative 3t over 2 or 3t over 2. Okay. So if I had more involved transformations, so the idea is very similar. Suppose we wanted to find x of 1 minus 2t for the same x that was defined before, when x of t is given by 2t for t greater than 0, negative t for t less than 0, that's equal to 0 for t equal to 0. Now to find x of 1 minus 2t, we simply replace t by 1 minus 2t. So we get 2 times 1 minus 2t. Again, for 1 minus 2t being greater than 0. Or equivalently, this implies that t is less than a half. And this is negative 1 times 1 minus 2t for 1 minus 2t less than 0, or equivalently for values of t greater than a half. And it's equal to 0 when 1 minus 2t is equal to 0, or for t equal to a half. Okay. Now that we have obtained some intuition about transforming signals that have been defined piecewise, we can state the general result about this. Now suppose I have a signal x of t that's defined piecewise. It's defined to be the function g1 of t for the range of values of t defined by some function h1 of t being greater than 0. It's defined to be g2 of t for the range of values of range of values defined by h2 of t being greater than 0, so on and so forth. And let us say we also have the signal x of t defined at m points for m specific values of t defined by hn plus 1 of t being equal to 0, so on and so forth, until hn plus m of t being equal to 0. Okay, so these just define the range of values of t, and these define the corresponding functions. Okay, Now the question is, if we want to transform the signal x of t, or we want to write an expression for x of f of t, where f of t defines the transformation. So for example, f of t can be negative t, f of t can be 1 minus 2t. These are the two examples we just looked at. So you can have many different transformations here. So generalizing the previous result, then x of f of t should be given by this is g1 of f of t for the range of values of t defined by h1 of f of t being greater than 0. And this is equal to g2 of f of t for the range of values defined by h2 of f of t being greater than 0, so on and so forth. So we can go up to the nth value, gn of f of t for hn of f of t being greater than 0. And of course we can then do the same thing for the equalities. Gn plus 1 of f of t when hn plus 1 of f of t is equal to 0. So on and so forth until gn plus m f of t when hn plus m f of t is equal to 0. Of course, what we can do is we can rewrite all these in terms of t being greater than 0 or t being less than 0, or perhaps some range of values of t depending on what these functions h's are.